Welcome to a new video about electric circuits. This is our example about the voltage divider rule. We will work out several examples and also the calculation step by step, and also verify these in SPICE simulations. So our first example number one, is the following. We have the following circuit given. You see here the DC source VSS and three resistors R1, R2 and R3. The values are shown here. We would like to calculate, the voltages V1, V2 and V3 as shown here. Now how can we do this for this example? There are many other ways, but we will use the voltage divider rule, which is actually much faster and also convenient in this circuit. What is the voltage divider rule? What we do is in the solutions you look actually at the part where you want the voltage between this node and that node, and for that you take the resistor. You place it here in the numerator, you divide by the complete set of the resistors in series, which is R1 up to R3. And then times your source resistor, which is in this case 9 volts. So you have now V1 directly. So we now substitute the values. It will be then 10 over the 10 plus 25 plus 40 as given in the example times 9 volts. And that will give you 1.2 volts. Similarly for V2. So V2 means actually between this node and that node, voltage between this and that node. That's again only the resistor where you find that between these two nodes, which is only R2. Then you get R2 divided by the complete resistors here, the complete set, which is R1 up to R3. So the series combination, just add them up, times Vs again. And then you can now use 25 over exact same value times 9. In this case you get 3 volts. The final one, which is V3, which is also similar to what we have done before. So again, now only R3 divided by the complete set times Vs, which is then 40 over the total resistance times 9. That will give us 4.8 volts. Now what you see here, there's actually an observation we can note here. The Vs here, the source voltage, is actually the summation of this V1, V2 and V3, which is actually logical because Vs is divided now in 3 parts, which is 1.2, 3 volts and 4.8 volts. So add them up, you will get indeed 9 volts. So this is actually verification for our calculations. Now moving on to the next step, which is the simulation result. We would like to check if this is really the correct one. So this is the simulation circuit in Tina TI SPI. You see again the Vs for the 9 volts DC voltage, R1, R2 and R3. The values are shown here, and here we use the voltmeter. You can see the 1.2, 3 volts and 4.8 volts. So all of them are checked, so we can see that we have verified our calculations. Okay, let's now move on to the example number 2, which is a little bit complicated example. You see here the Vs, again a different voltage source, which is 7 volts here. We have again 3 resistors, but in this case we have this R1 here, and now the R2 and R3 are parallel. There are some different values for the resistors, and again we would like to calculate the voltages V1, V2 and V3. So what we can do here, let's see. Now the solutions, we first recognize in our calculations that the V2 and V3 are parallel. And since 2 voltages are parallel, or 2 nodes are parallel, we can say the voltages are equal. So we can say V2 is equal to V3. So we can take this together and also call this a new resistor, which is called now here, for example, Rx. I just called that Rx. Now we can now find the equivalent resistor here by using the parallel resistor formula. So we can first transform this to a more convenient, easy circuit. You see again a Vs, R1, but now here the Rx, which is still to be determined, and that is the voltage here across this Rx, which is called now Vx at this node X. What is Rx? Rx is the parallel combination of the resistor R2 and R3 as shown here. That is given by this notation, which is also calculated using just 2 resistors, R2 times R3 over R2 plus R3. We know it is 10 times 15 over 10 plus 15, and when you now do the calculations you get 6 ohms exactly. So this is effectively, these two effectively make 6 ohms. Okay. We also then say that Vx, which is this voltage, is also V2 and V3. It doesn't matter which one you take, but that is also what we can define here. Now, we can move on and then again use the voltage divider rule here as our powerful method, as V1, which is this voltage, actually this voltage in this case, is equal to R1 divided by the complete resistor, which is R1 plus Rx, that's shown here, times Vs, which is 7. So we can now calculate that because we already know the Rx, and now we have here 2.8 volts. In a similar form, we can now calculate Vx. Now we only need to look at here. We know Rx, so it is Rx over, again, the complete resistor, the value, so that's the series combination, times Vx again, times 7. So we get now 4.2 volts. Again, V2 and V3 are also 4.2 volts. So that was actually a question in place here. So V1 is known, but V2 and V3 is also known because Vx is 4.2 and that is equal to V2 and V3. Again, the note, we can say Vs is equal to V1 plus Vx. That's actually in the circuit already given because this voltage will be then divided in this part and that part. That's actually shown here, so it will be then again 7 volts. That is the verification for this calculation. Now, looking at the simulation results, this is the simulation circuit in Tina TI Spice. You see again this Vs of 7 volts, R1 of 4 ohms, and also R2 and R3. You see the voltmeters and you see the readings here, which is actually exactly as we have calculated. So we can say this is all checked. Okay, moving on to our example number 3, which is our final example in this video. We have now a little bit more complicated circuit. We have now 4 resistors, R1, R2, R3 and R4. And we have one DC source still, Vs, which is 9 volts. And we have also some values for the voltages. So this voltage across R1 is 5 volts, V1. Across R4, V4 is 6 volts. So there are some values given for the voltages, but there are also values given for the resistors. R2 is this voltage, this resistor is 20 ohms, and we know the summation of these two is 75. We don't know the independent values, but we know it must be total 75 ohms. So what we like to calculate is the following, which are the 6 values unknowns here, which is V2, the voltage here, V3, which is the voltage there, VAB, which is between this node and that node. That is interesting, we will see that shortly. R1, that's a resistor, R3, and also the R4. Okay, let's see what we can do for this example. Solutions. First, the calculations for the first step. We recognize that this branch and this branch is parallel to the voltage source Vs. That means the Vs is V1 plus V2 and also V3 plus V4. So that is actually what you can say. Then together we can say, since this is Vs, this is also Vs, we can say V1 plus V2 is equal to V3 plus V4. Now we can use these equations easily for calculating the V2 and the V3, because V2 here from this equation is Vs minus V1. And that's 9 minus 5, which is then 4 volts. And from this equation we can say the V3 is equal to Vs minus V4, that is just 9 minus 6, which is 3 volts. So we have actually 2 of the 6 unknowns already for this example. And we can now calculate also VAB, because this voltage between this node and that node, which is actually VAB, which is VA minus VB. Now the voltage at node A is actually the V2, and the node voltage at B is the voltage V4. That is referred to ground. So we can say V2 minus V4, which is 4, we already calculated here, minus 6, which is given, is then 4 minus 6 is minus 2 volts. So between these two nodes you have actually minus 2 volts. Fine, now we can calculate now the other parameters using again voltage divider rule for each branch. I will now use this branch, which is then V1 is equal to R1 over R1 plus R2 times Vs, and this relationship can be used now to calculate the unknown R1. How? Now let's first substitute the values we have. V1 is 5 volts, R1 is unknown, R2 is known because it is 20, and we also know that the Vs was 9. So we have now here an expression which is the only unknown here is R1. So we can divide now the left and right hand side by 9. You get now 5 over 9. Cross multiplication, that's the next step. So 5 times this, 9 times the R1, you get this one. Now work out the parentheses, you get now 5 times R1, 5 times 20 is 100, is 9 times R1. And effectively this 100 is equal to 4 times R1. That means R1 is 100 over 4, which is 25 ohms. So that is also done. The next one is, since we want to know the R3 and R4, we can look at the voltage here because that's known. So we can again relate that using the voltage divider rule. V4 is equal to R4 over R3 plus R4 times Vs. And then we know that this is 6, so 6. And this is R4, which is unknown, but we know the summation here, which is 75, so that's nice. And times 9, so we only have here unknown, which is R4. Again, divide by 9, left and right hand side, so you get now 6 over 9 or 2 over 3 is equal to R4 over 75. Now cross multiplication, this will give you 6 times 75 will give you 450. And this is 9 times R4, that means R4 is now 50 ohms, exactly. Now, since this is 50 ohms, and we know that the summation is 75, that means R3 must be also 25. So we also know all these resistor values, R3, R1, and R4. Okay, let's now look at the simulation result. This is now again the circuit in the SPI simulator. You see the 9 volts, resistors, and also the voltmeters here. All actually according to the values given and also what we have calculated, because this is 5 volts V1, this is 6 volts V4 which is given, and we have calculated for V2 which is 4 volts, it's actually shown here, and V3 was 2 volts, so shown here, and VAB between this node and that node is -2, also verified. We also have used the R4 and R3 and also the R1 value we have calculated. So that means this is also checked, so it's according to specifications. So this is the complete set about our voltage divider rule example for these circuits using DC voltage sources. If you have any questions, comments about these examples, please let me know and I will try to answer them as soon as possible. See you next time in another video.